Hello again, and welcome back to our discussion about elimination reactions. This is part 2 of our videos, so if you haven't seen the first video, go back and watch that first. That sort of tells you the basics, and we're going to go into one more detail here. All right? So just to make sure we're back in the right context, the first thing we talked about in the last video was E2 reactions and what they are. Basically, it's what happens when you have a substrate, an R with a leaving group like Br, you have a strong base, and then you want to make a double bond. And remember, we're going to add heat to this reaction to make it work better. Also, we mentioned that this reaction is an E2 reaction because it has a strong base, and the mechanism happens in only one step. So in that mechanism, we redraw the base as a minus charge. It comes to get the hydrogen. When the bond breaks to the hydrogen, instead of going to the carbon, it goes to the double bond to make the double bond, and then the leaving group leaves, all in one step, and that's what makes it E2. If that doesn't look familiar, you should go back to the other video and watch it in more detail. So the other thing we want to remember is that we said that sometimes there's a choice of products and we need to know that. So for this example here, we said eliminations are regiospecific, so there's one product that's going to be formed. This is going to be the major product here on the left because we're using this sodium ethoxide. Because that's considered a small or skinny base, that's going to be the major product. This major product happens to be Zaitsev's product, which is the most stable double bond of the choices, right? We can only have a double bond that is attached to the carbon with the bromine. There's no rearranging for an E2. So it's either got to be to the left, to the right, or to the bottom, and those are the only choices we had. The other thing is, if this is the major product, that's all you would draw for a box question. So if you have sodium ethoxide, you would draw this thing in the circle here and not draw the minor product. So we'll just cross that out for now, okay? So now what we're going to do next is compare this to using a different kind of base and see why it's different. So as we just said, if we use sodium ethoxide, a common base, we're going to get the most substituted double bond, the most stable one. But what happens if you want the other alkene? Remember I told you that organic chemists love to have every option possible. So if there's one way to make one thing, they want to find the way to make the other thing. So basically that's what they did. So if we want to get this same substrate we had before and have it make the less substituted double bond as the major product, the thing we need to use is called the bulky base. So the bulky base looks like this. So it's T-butoxide. Basically, it's just a more bulky version of an alkoxide. And then we're going to use T-butanol, it's just the solvent. Basically, it's just the same thing with the hydrogen on it. I showed it over here. And then we're still going to heat it, all right? So basically, that's all you have to do. The reason that this works is because of the bulkiness. So whenever we have the mechanism before, remember we had the hydrogen was being taken away at the same time as the Br was leaving. So that means that the base has to be able to get in there close to where the Br is. Well, if you're a bulky base, it's actually kind of hard to get here. So if you look at this carbon 2, you've got hydrogen here that I want to take, but you've also got a methyl here that's got hydrogen sticking up, and then you also have these other methyls sticking all around, right? So it's just kind of crowded and hard to get to. So if I try to take one of the hydrogens off of this carbon here, carbon 4, that's actually easier. Not only is it easier because there's less bulk around it, because there's not as many things surrounding that carbon because it's at the end, but also because there's more hydrogens to pick from, right? On this spot here on number 2, I've only got 2 hydrogens. Here I have 6 different hydrogens that I can remove and still get the same product. So just like the chances of me coming up to the right hydrogen are more, so it's kinetically favored as well. So that's why this is the major product when you use a bulky base. Now, just to be sure we're clear, we also want to be able to draw the mechanism for this. So because it's a strong base, it's still going to be an E2. So this is not an E1 situation. It's going to be E2 because it's a strong base. So let's draw what that looks like. Okay, so I'm going to redraw the reaction down here so we have some space. And then we're going to redraw our base because it's strong. So let's draw that here with the minus charge. And then it's going to take off a hydrogen. So what hydrogen do we need for the product shown? Right, it's going to be the one on carbon 4. So just come and take that. Then the bond breaks to make the double bond, and then the bromine leaves. So just like before, it's all one step, 3 arrows. Okay, so hopefully that makes sense. That's all we have to talk about right now. The main difference between these two is going to be for box questions or for synthesis. That's when you're going to use these differences. But the mechanisms are actually the same. So hopefully this helps. Now we're done talking about all the basics of elimination, and then we can have more class time to talk about any questions you have on this, but also some more specific examples and stereochemistry stuff. All right? So hopefully you enjoyed it. There'll definitely be activities on these as well, so make sure you check that out after we talk about it in class.